All right, good evening and thank you for listening. We will be looking at a time series forecast of U.S. national healthcare spending, beginning with the data and its background, and then moving on to time series plots of the data, and then our forecasts. Our data comes from the Centers for Medicare and Medicaid Services, a government agency. The data ranges from 1960 to 2019 and covers figures like the total amount spent on healthcare every year, the total as a percentage of GDP, and the percent change year on year. The government provides this data as well as forecasts, in this case for the next 10 years. And as we can see, the figures are pretty substantial. Healthcare accounts for the single largest expenditure of in any industry in the U.S., and that is set to increase from 3.7 trillion a couple of years ago to about 6 trillion in 2028, according to these government forecasts. And the government also expects spending to increase at about a constant 5% rate per year. And Medicare is actually increasing at a faster rate, which suggests that as the population ages, the share of our income that we spend on healthcare will continue to increase, and therefore forecasts such as these will be essential to managing and planning for the impact of our healthcare needs on the economy. So we begin by plotting the data, and as we can see, we have an upward trend that is increasing, and as we model this data, we are going to need to account for that shape and the trend. And in addition to the total expenditures, we will also be briefly looking at and forecasting, again, the expenditures as a percentage of GDP, and also the year-on-year change, which, as we can see here at 2019, was about 5%. The first forecast we will be employing is the random walk with drift. As we learned, this is one of the simplest forecasts, which in many cases can be accurate and very useful. However, as we can see here, after modeling the training data set and then applying the model to the test data set, our forecast deviates from the observed values from 2015 to 2019 pretty much immediately. Even the confidence intervals do not include those most recent values. And so even though the forecast looks completely different if we do not use a training data set and if we instead forecast based on the most recent values, we are going to look for a more sophisticated model that can account for the increasingly aggressive trend and perhaps better reflect the trend that we're already seeing. And so to do that, we will first turn to exponential smoothing. There are various forms of smoothing, as we have seen, and in this case we need a model that accounts for the upward trend and can account for historical data going back at least a few years. And as you can see here, the situation relative to the previous model is completely different. It's the opposite, where the forecast is actually more aggressive than the observed values in our test data set. And so even though this model is more accurate than the previous one, I think we can do a little bit better. So our first model here exponential smoothing model rather, is Holt's linear trend, you're going to now use the ETS function in R to automatically select a model. And as we can see here, the automatically selected model is quite a bit more interesting than the previous one, such that the confidence limits are much more narrow. The trend is much more in line with what we have seen over the last 5 to 10 years. And even though this model has dramatically improved on the previous one, there are still some changes that we can make. And so as we can see here, this model has chosen a multiplicative error, which is good. That's what we want. There is no seasonality component. However, it has selected this A here in the middle is referring to the trend, and it has selected an additive trend. But as we can see, because of the shape of the plot here, it may be more appropriate to go for a multiplicative trend. So the next step is to manually select that model, and that's what we see here. And this forecast seems to better capture the upward curvature in the recent observations. And here we're only forecasting out 5 years, but in this next slide we can see a forecast going out to about 2028. And this model seems to offer the best results so far because it reflects the forecast that we see from the government. So again, government expects healthcare expenditures to reach about $6 trillion by 2028. And as we can see here, that lies very, very close to the line in our forecast and well within the confidence limits. And applying an automatic ETS model selection to the expenditures as a function of GDP, we can see that by 2028, it'll reach about 19–20% of GDP, which is exactly what the government expects. And we expect a pretty consistent 5% change here every year, 5% increase, and that's what we see from the government's analysis. And so this model seems to offer the best results out of these three. And if we were to provide these forecasts to a client, let's say, we could hardly do worse than all of the apparatus of the government that has put behind it has put behind its own forecasts. And so, to sum up, the drift method systematically underestimates values, the observed values rather, in our training and test data sets, while the Holt model overestimates its forecast. And the ETS model automatically selects an additive trend component, and our best model seems to come when we force the multiplicative trend in addition to the multiplicative errors. That model seems to fit the best, and it produces forecasts that closely resemble the government figures. And as impressive as these figures may be, only time will tell whether we overestimate or even perhaps underestimate the spending on healthcare as a result of the aging population in the US and perhaps other factors. So ultimately, the ETS function provides an extremely accurate and optimal forecast, and if we were to forecast these values for a client, that is what I would go with. So thank you for listening, and enjoy your summer.